So in this video, I want to go over the difference between electric potential versus electric potential energy. They're not the same. They sound similar, but they're not the same. This is a type of energy, like gravitational potential energy or the energy in a spring. Electric potential energy is simply a type of energy. However, electric potential is something very different. So what is electric potential? Well, first, let's imagine we have this particle with a positive 10 coulomb charge. We know coulomb is the unit of charge, so let's say we have this particle with the positive 10 coulomb charge. Due to this charge, it's going to create electric potentials. For example, at this particular point, it's going to have a certain electric potential because of this charge. And also at this particular point, it's also going to have its own electric potential because of this charge. This charge creates these electric potentials. And I know it seems like an abstract idea, but essentially, electric potential is a characteristic of a region in space. This particular spot has its own particular electric potential. This spot has a different electric potential. This spot has a different electric potential. And this spot has a different electric potential. It's just a characteristic of a region in space. So again, due to this charge, it's going to create these electric potentials. However, how do we determine exactly what the electric potential is at this particular point? So let's say we're interested at this particular point, and we know this positive 10 coulomb charge is going to create these electric potentials. But maybe we're interested in the electric potential specifically at this particular point. How do we determine that? Well, to determine the electric potential, we simply use this equation. K is just Coulomb's constant. Q is the magnitude of the charge that's creating the electric potential. We know this charge creates the electric potential, so therefore the magnitude of this charge impacts the electric potential. So it's important, so therefore it's in the equation. And then R is the distance. So for example, maybe we have a positive 10 coulomb charge particle, and we're interested in the electric potential, maybe this distance. Maybe this distance represents 9 times 10 to the 9 meters. So we have a positive 10 coulomb charge, and we're interested, what's the electric potential in 9 times 10 to the 9 meters away? What's the electric potential at this particular location? Again, we just simply use this equation. And if we were to plug in our values and our units, we would get an electric potential of positive 10 joules per coulomb. So now we know the electric potential at 9 times 10 to the 9 meters away from a positive 10 coulomb charge, so the electric potential at that particular spot has an electric potential of positive 10 joules per coulomb. So now we know the electric potential at this particular spot is positive 10 joules per coulomb. And notice the units. This isn't charge. It's different. It's just a characteristic of a region in space, and these are the units. But let's do another example. Let's say we're interested in the electric potential at this distance. Again, we know this positive 10 coulomb charge creates these electric potentials. So now we're interested in the electric potential at this particular location. How do we determine the magnitude of the electric potential at this location? Again, it's that simple formula. If we want to determine the electric potential, first we need to know the magnitude of the charge that's creating the electric potential. So we know that's important. And we need to know the distance that we're interested in. So let's say this distance represents 9 times 10 to the 10 meters. So if we have a positive 10 coulomb charge, what's going to be the electric potential 9 times 10 to the 9 meters away? What's going to be the electric potential at this particular location? Again, we just simply use this equation to determine the electric potential. So we have a positive 10 coulomb charge, and we're this particular distance. So if we plug those in, we would get the electric potential as positive 1 joules per coulomb. So now we know at this particular location, it has an electric potential of positive 1 joules per coulomb. So now we know. And again, what is this? Why do we care about this electric potential? What does it mean if this region has an electric potential of positive 10 joules per coulomb? Well, the way I like to think of electric potential is if a region in space is high in electric potential, it's high in positiveness. It's high in electrical positiveness. And that's just the way I like to think about it, and that's just the convention humankind has used. So this particular location is high in electric potential. It's relatively high in positiveness. We have a positive 10. So that's relatively positive, while this region is lower in electric potential. It's lower in positiveness. It's only positive 1 joules per coulomb. And maybe this region right here will have a very high electric potential. This particular spot will be very high in electric potential, very high in positiveness, maybe a positive 100 joules per coulomb. But again, electric potential is just a characteristic of a region in space. This particular region has a certain electric potential, and we have these electric potentials due to these charges. These charges create these electric potentials. But something important to realize, and the key point of this video, is whenever you know the electric potential at a particular spot. So we know at this particular location in space, it has this particular electric potential. However, whenever you know the electric potential of a certain region in space and you throw in a charge, so if we know the electric potential of this particular spot is positive 10 joules per coulomb, what would happen if we threw a positive 3 coulomb charge on that region of that particular electric potential? Well, now we have a system with energy. And that's the key point of this video. If you know the electric potential in a particular region and you throw in a charged particle, now you have a system with energy. Exactly how much energy would we have if we had a positive 3 coulomb charge in a region of positive 10 joules per coulomb electric potential? Well, you simply just multiply them. We multiply them, the coulombs cancel, and now we have joules. So now we know if we have a positive 3 coulomb charge and a region of electric potential of positive 10 joules per coulomb, now we have a system that has 30 joules of energy in the form of electrical potential energy. So now we have a system with energy in the form of electric potential energy. So again, that's the key point of this video. For example, maybe we have this region with this particular electric potential. What happens when we have a region with a particular electric potential and we throw in a charged particle? Now we have energy. So again, how much energy would we have if we threw this positive 3 coulomb charge at this particular location? Well, again, we know we just multiply them. We have a positive 1 joules per coulomb electric potential that we threw in a positive 3 coulomb charge. We multiply them, coulombs cancel, now we get joules. Now we have a system with energy. And again, whenever you throw a charge in a region of electric potential, now you have a system with energy. And this particular system, with the 3 coulomb charge in this particular electric potential, this system has 3 joules of energy in the form of electric potential energy. So now this system has 3 joules of energy in the form of electric potential energy. But something important to realize is, remember, and then you might wonder, what happens if we have a positive charge? Let's say we have a positive charge and then we threw in another positive charge. What's going to happen? We know they're going to repel. We know this charge is going to repel and it's going to move away. Why? Why if we have these 2 positive charge particles, why are they going to move away? Well, we see, for example, with this positive charge particle, when we threw another 3 positive charge particle here at this particular location, we had a system with 30 joules of energy in the form of electric potential energy. However, if instead of having that 3 coulomb charge here, instead of that 3 coulomb charge was here, again, we know if the 3 coulomb charge was here, we would have a system with 3 joules of energy in the form of electric potential energy. So that explains why a positive charge particle would want to move in this direction. That's why this positively charged particle would want to move away. It wants to move because when the positive charge particle is here, we have a system with 30 joules of energy in the form of electric potential energy. However, as this charged particle moves towards regions of lower electric potential, we have a system that goes to a lower energy state. When the charged particle is here, we have 30 joules of energy. When the charged particle moves here and now it's here, now we have 3 joules of energy in the form of electric potential energy. So as that positive charged particle moves in this direction, the system goes to a lower energy state. We go to a lower energy state. And again, so that's the exact same reason why if we have a box and we lift it high in the sky, we have a system, this box has energy in the form of a gravitational potential energy. However, what's going to happen? We know that box is going to fall. Why does it fall? Because as it falls, it goes to a lower gravitational potential energy state. That's why it falls. As it falls, it has less energy in the form of gravitational potential energy. It goes to a lower energy state. For that exact same reason is why this positive 3 coulomb charge would want to move in this direction. Because as it moves in this direction, the system goes to a lower energy state. And something important to realize is positively charged particles always like to go to regions of lower electric potential. Remember, what's the definition of, or how do we like to think of electric potential? I like to think of electric potential as electrical positiveness. This region, we said, was relatively high in electric potential, positive 10 joules per coulomb. We said this region was lower in electric potential, lower in electric positiveness, less positive. So again, that explains why this positive 3 coulomb charge particle goes towards regions of lower electric potential, because as it goes towards a region of lower electric potential, it goes to a lower energy state. So now let's do another example. Let's say we had a negative 3 coulomb charge that we threw in this particular region of electric potential. What happens when we throw a charged particle in a region of electric potential? We get a system with energy. So how much energy would we have? Well, again, how do we determine? We just multiply them. We know this particular region has this electric potential, so we threw in a negative 3 coulomb charged particle in this region of electric potential. We just multiply them. Coulombs cancel, and now we have negative 30 joules of energy in the form of electric potential energy. So when we throw a negative 3 coulomb charge in this region of electric potential, we have a system with negative 30 joules of energy in the form of electric potential energy. However, what would happen again if we threw instead the negative 3 coulomb charge here? Instead, what would happen if we threw it here? Well, we know we would have a system with energy. How much energy? Well, again, if we throw in a negative 3 coulomb charge in a region of this particular electric potential, now this system would have negative 3 joules of energy in the form of electric potential energy. So we know what happens if we have a positive charged particle and a negative charged particle. We know they're going to move towards each other. We know they're going to want to move towards each other. Why? Well, we know when the negative 3 charged particles here, we have a system with negative 3 joules of energy in the form of electric potential energy. However, as it moves, once it gets here, we would have a system with negative 30 joules of energy in the form of electric potential energy. So as this negative charged particle moves, it goes to a lower energy state. This is relatively more negative, so it's a lower energy state. And so another key point is negatively charged particles always like to go to regions of higher electric potential, regions of higher electrical positiveness. But again, remember, electric potential is not charge. It's different. So that's why we have this negative charge particle wanting to move in this direction. Because as it moves, the system goes to a lower energy state. So positive charge particles want to go towards regions of lower electric potential. However, negative charge particles like to go to regions of higher electric potential. But something else important to realize is we already explained how this positive 10 coulomb charge essentially creates these electric potentials. There's a particular electric potential here, and it creates a certain electric potential here, and it's contributing to these electric potentials. However, what if now we also threw in a negative charge particle? Now, what if we threw in a negative 10 coulomb charge particle? It's also going to create electric potentials. It's also going to contribute to the electric potential here, and it's also going to contribute to the electric potential here. And let's assume this is symmetric. So let's say this distance is the same as this distance, and etc. Let's say this is symmetric just to keep things simple. But the point is, for example, let's focus on this particular location, this particular spot right here. We know this positive 10 coulomb charge contributes to the electric potential here, and it contributes positive 1 joules per coulomb of electric potential. However, this negative 10 coulomb charge also contributes to the electric potential at this particular location. And this negative 10 coulomb charge contributes at this particular location negative 10 joules per coulomb of electric potential. And again, how do we know exactly how much electric potential this charged particle is creating at this particular location? Again, we just use our formula. The electric potential equals Coulomb's constant multiplied by Q divided by R. So again, if we know the magnitude of this charge, and we know this distance, and we plugged in those values, we can determine what electric potential it's contributing. This electric potential it's contributing. But again, the point is, we know we have these two charged particles. We have a positive 10 coulomb charged particle and this negative 10 coulomb charged particle. They're both contributing to the electric potential at this particular location. So what's the net electric potential at this particular location? Well, this guy contributes negative 10 joules per coulomb. This guy contributes positive 1 joules per coulomb. So the net electric potential is negative 9 joules per coulomb at this particular location. And again, if you were to do that same thing here, this guy contributed positive 10 joules per coulomb. This guy contributed negative 1 joules per coulomb. So the net electric potential here is positive 9 joules per coulomb. But again, remember, the way humankind has defined electric potential is positiveness. So this region is high in electric potential, higher in positiveness. This region is lower in electric potential, lower in positiveness, and in fact, it's on the negative side. So we have this difference in electric potential. We have a voltage, this difference in electric potential. But again, it's these charges that contribute to the electric potential here. And really, at the end of the day, this electric potential tells you about the energy if you threw in a charge at that particular location. That's the utility of it. So for example, let's do an example. We know we have this region of space with a net electric potential of negative 9 joules per coulomb. What would happen if we threw a negative 4 coulomb charge in this particular region of this particular electric potential? We know we have a system with energy. How much energy we know? We just multiply them. The electric potential is negative 9 joules per coulomb. We threw in a negative 4 coulomb charge. We multiply them, And now we would get a system with this much energy, 36 joules of energy in the form of electric potential energy. So that's what would happen if we threw in this negative 4 Coulomb particle right here. We would have a system with this much energy. However, what if instead we threw that negative 4 Coulomb charged particle here in this particular location? Well, you could do the same operation, and now we would have a system with negative 36 joules of energy in the form of electric potential energy. So that explains, and we know from common sense, if we have a positive charge and we have a negative charge, what would happen if we threw a negative charge particle right here? We know we would move in this direction. That makes sense. That's common sense. Why? Well, again, we know when the negative 4 Coulomb charge particle is here, we have 36 joules of energy in the form of electric potential energy. But if it were to move here, we would have a system with negative 36 joules of energy in the form of electric potential energy. So as it moves, the system goes to a lower energy state, a system with less energy in the form of electric potential energy.